All right. We've talked about counting and looked at counting and seen what we can do with that. We're now ready to start actually talking about probability. And before we start doing things and working with it and making calculations, we're going to have to ask ourselves, what does it actually mean? And how do we deal with this? And one of the key issue is we're discussing things that happen. And the things that happen we're going to refer to as events. And we're going to talk about how do we decompose events into different unions. What is an event? And we want to know how do we interpret these things. And the question we're going to ask is, given an event, how likely is it to happen? So we'll spend a little time just talking about events and then start getting into this idea of probability. And that word turns out to be complicated. But having said that, that word right there, event, oftentimes tends to cause a good deal of confusion. So let's just look at an example. Let's roll a six-sided die. And if that's fun, we're going to roll again. And we're going to have to make all kinds of assumptions and think about what's going on here. And it can be a bit tedious, and I'm going to skip it at times just because it takes too much time and can get lost. But we're going to assume that the die is fair, so that means the six sides are equally likely. It means that there's a different number on each side. And we're going to assume that they're independent. Now, there's a mathematical definition for that word, independent. But for now, it just means that if I tell you something about the first roll, that doesn't give you any information for the second roll, and vice versa. If you know something about the second roll, that doesn't tell you anything about what happened for the first roll. And we're going to use that idea to try to define that word. So the question is, what could happen? And the key word there is could and happen. So in this case, if we look at the two rolls separately, I get a 1, 2, 3, 4, 5, or 6. Those are the potential outcomes. For the second roll, again, I get 1, 2, 3, 4, 5, or 6. But I'm worried about what happens for the two rolls together. So if I roll a 1 the first time, I could roll a 1 the second time. If I roll a 1 the first time, I could get a 2, or a 3, or a 4, or a 5, or a 6. If I roll a 2, I could get a 1, a 2, 2, on and on. So in terms of what could happen, these are all the possibilities here, is that I could get, for example, I could roll a 3 first and then a 3 second, or a 3 first and a 4 second. And I want to know how to interpret this. Now, what if we changed it and we change it to this? I roll the die twice and add the numbers. Well, if that's the case, what could happen? I could get a 2, a 3, 4, 5, all the way out to 12. Now, this is going to be a little bit different than looking at it in terms of this, because there's only one way to get a 2, but there's 2 different ways to get a 3, and there's 4 ways to get a 4, and each of these particular things is not equally likely. Whereas the way I've decomposed things here, everything is equally likely. So it may be better for me to, instead of thinking like this, think about in terms of the actual events that could happen, and then I can interpret each one of these things in terms of my outcomes. So if that's the case, now if I think of these events instead of just these discrete events, if I think of them in terms of these particular outcomes, now it's a little easier to think about 7 if I get a 4 than a 3. But notice how many ways can I get a 7? There's 1, 2, 3, 4, 5, 6 ways to get a 7. Only one way to get a 2. So just intuitively, it seems like I'm more likely to get a 7 than a 2, and you might expect to get roughly 6 times as many 2s if you do this many times. Again, that's very rough, and that's not guaranteed to happen. But the key thing is, in terms of my outcomes, the way if I describe this as the sum of 2 numbers after I roll a 6-sided die, these are my outcomes. But if I go back and decompose the situation into all possible events that could happen, then I can think of my outcomes in this form. So for example, here, the set Aij is the situation where I roll an I first, then roll a J second. So this right here would be A5, 4. Okay. Now, a couple of key things here that are important in terms of this definition. I've got these Aij's, and I can be between 1 and 6, and J can become 1 and 6. And the thing to notice is if I look at A13 and A31, then there's no overlap. These are different events. And so the intersection is empty. Same thing with 2, 1 and 1, 2. That intersection is empty. A2, 1 and say A4, 3 is also empty. So if I take any Aij and compare it to Mn, this intersection is going to be empty if I is not equal to M or J is not equal to N. So I've taken my set of all possible events and I've expressed it in terms of these events. The union of all of these events gives me everything that could happen, and each individual event is disjoint from the others. So sets that don't overlap, we call them disjoint. Right. So as an example, let's let the event E be the sum is even. And now I can write this as the union, 1, 3, of the situation where I get a roll of 1 and a 1, a 1 and a 3, a 1 and a 5, or a 2 and a 1, 2 and a 2, 2 and a 4, 2 and a 6, or 3, 1, 3, 3, 3, 5, or 4, 2, 4, 4, 4, 6, or so it's 4, 5, 1, 5, 3, 5, 5, and finally I could roll 6, 2, 6, 4, or 6, 6. And if I do any one of those things, I'll get an even sum. And notice I've written this E as the union of a set of disjoint events. Okay. And notice there's 18 of those. There's 36 total events that could have happened. And this is going to be a big if. If each event is equally likely, we would expect about 18 out of 36 times to be even. Whatever this word expect means. Okay. Now here's the thing is if I do this 36 times, so 36 times I roll the die twice and add up those numbers, I'm not guaranteed that 18 times I'm going to get an even amount. In fact, that's probably not likely. But if I do this over and over and over again, we would expect that to be happening in the long run. Okay. So question comes up is, how do we visualize this? Because looking at things like that is really confusing and not helpful. Is there another way to do this? The answer is yes. One is a Venn diagram. The idea is I've got my sample space. And now I'm going to partition it in terms of my possible outcomes. So if I think of this as roll 1 vertically and roll 2 horizontally, for the first roll I could roll a 1, 2, 3, 4, 5, 6. For the second roll I could roll a 1, 2, 3, 4, 5, 6. And now if I roll a 1 and a 1, that would be a 2. A 1 and a 2 would be a 3. And I can just keep this up and fill in the rest. So for example, if I roll a 5 first and a 6 second, that's going to be an 11, and it's going to be that square there. Okay. And now if I think about the even numbers, that's going to be here, 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 or here, here, here. And just if any one of these squares is equally likely, right, I can think of this as half of the squares are shaded, so half that area is going to give me an idea of how likely that is to happen. Okay. All right, so as an example, suppose I'm looking at the event where the sum of 2 rolls is less than 4. So that would basically be those 3 events. So if we call that event B, that's going to be A11 union A12 union A21. Okay. In terms of notation, we can ask what is the complement? So the complement is going to be where the sum of 2 rolls is 4 or more. And that's important because of that word less. And this is going to be what we call the complement. And so this is going to basically be all the sum of the union of the rest of the these A's. So then I would get A31 union A41 union A51 union A, 6, 1, and just keep on going until I get down to the end. In terms of notation, some people call that the complement, or use a C as a superscript. Some people put a bar over the top and call that the complement. Whatever, just be ready that different people use different notations, and that's okay, and just be prepared for that. Okay. Another way to visualize this is with a tree diagram. And the idea here is before I do anything, I can start in my base case. Now I roll the die. I can get a 1, 2, 3, 4, 5, or 6. And then after I do that, and when I roll the next time, I can get a 1, 2, 3, 4, 5, 6. If I roll a 2, I get a 1, 2, 3, 4, 5, 6. And just keep on going that way. I'm not going to do that because it's going to be a mess. But now to interpret this event here, this says I roll a 1 first, and then a 1, so that would be a 2. If I interpret this event here, this means I rolled a 2 first and then a 3, so that would be a 5. Okay. So for example, if I'm interested in all the possible ways to get a 5, well, see, I could do a 3 and a 2. I could do a 4 and a 1. So this would be a 5. I get a 1 and a 4, so this would be a 5. So there's 4 ways that I could get a 5. So the probability that the sum is 5. In this case, is going to be 5 out of the 36 times. Now, so I just introduced new notation, and I used the P word. What does this mean? So P, I'm going to call this the probability an event occurs, which means that whatever goes in here is the event. So this is going to be very strange. The thing that goes inside here is not a number. It's not a letter or anything. It's an event, whatever that means. So the domain of this is basically some possible outcome in some experiment or situation. And this number, we're going to say, has to be between 0 and 1, and is some measure of how likely the event is to actually occur. Whatever that means. A big question, though, is oftentimes it's very common for things to get new information up to the lead before the event occurs. As we get new information, that may change our interpretation of what this probability actually is. So the question is, as we get new information, how do we incorporate that information into our estimations? And the thing is we have to be able to do this in a rational and consistent way. So let's look at an example. So I'm going to roll a die. It's going to be 6-sided, fair, and it's going to be independent of anything else. I'm going to record a 1 if even, and if it's odd, I'm going to record a 0. Then I'm going to roll again. I'm going to add 1 to the result if even, otherwise I'm going to add 0. So how do we look at this? Well, for our Venn diagram, 4 things could happen. So if I roll an even first or an odd first, and then second, I could do even or odd. So for an even, I'm going to get 1, 1. So the result's going to be 2. Even odd's going to be 1, 0. So the result will be 1. Odd, even will be 0, 1. Result is 1. Odd, odd, 0, 0. So the result is 0. In terms of the tree diagram, I could get an even or an odd for the first roll, and then for the second roll, I could get an even or an odd. And that's going to be true regardless of what I get above. So if I get an even first and an even second, this is going to be a 2. If I get even odd, it's going to be a 1. Odd even is going to be a 1. Odd odd is going to be a 0. Okay. Now notice from my Venn diagram, I could have also done this. So my options are 0, 1, or 2. That's a perfectly valid Venn diagram, and it's correct. It's not necessarily useful because getting a 1 is not the same likelihood as getting a 0, 2. In fact, I'm twice as likely to get a 1 as a 2 or a 0. So if you look at it this way, that can actually be misleading, even though it's perfectly correct, and it may not actually be helpful. What happens though if I know the first roll was even? And the key thing to recognize is that once I tell you something about the situation, it changes our interpretation of what could occur. So if I tell you the first roll was even, that means this is still possible, and this is still possible, but this is out. Likewise over here, this is possible, this is not possible. So in terms of what could happen, it's what's going on here. So what we now have is, if the first is even, our situation now is either we're going to get a 1 or a 2, or if I think of it as a tree diagram, this is what's going on. And so now the likelihoods that I get a 1 or 2 are going to change. In fact, the likelihood that I get a 0, that's not going to happen. Okay. All right. Okay, so I still haven't really defined what this word probability means or likelihood. And so the question is what do these even mean? And this is a really important question because people use these tools literally when money's on the line, right? And also, if you're making medical decisions, you're making decisions that impact people. So this is kind of important to get a good feel for what these things actually mean. And one of the issues here is that it's intuitive, but it's also not really well defined, which means that our intuition can mislead us. And it's actually hard to actually define. So there's 2 views. One is the objectivist view. And the idea here is that probability is the relative frequency that something might happen after a huge number of trials. And so this is not really well defined, but it's also intuitive, and it's kind of implies some kind of limiting process. So example, if I roll a die, I'm going to record whether or not it's even or odd. We would expect about half the time even, about half the time odd. So if I do this 5,000 times, according to this means that I'm going to get it 2,500 times, going to be even, 2,500 times going to be odd. But if you do it 5,000 times, that's actually extremely unlikely that you get exactly 2,500 evens and 2,500 odds. We would expect, though, that about 2,500 times will be even. So if we get 2499, we won't be surprised. If we get 2460, maybe we shouldn't be surprised at that either. But there's really no guarantees. We have no idea what's going to happen. And in fact, the question here is problematic because it's really not what's happening in the limit, and this is just a rough estimate. Okay. The other point of view is the subjectivist view. And the idea here is probability is a personal belief that measures how you feel, how likely something is, or something will be. Okay. So if I roll two fair, independent, six-sided die, I think that the probability is the sum of two. There's only one way that could happen, and there's 36 ways total things. I think that's going to be about 1 out of 36 times. Okay, my point of view may change later, but that's what I think is going to happen. The key thing about this is our perception can change as we get new information. And the key takeaways here are we need to be really careful. We should be skeptical. And the way we interpret these things and think about these things is really tricky. It's also really important to acknowledge the notation kind of sucks. And then finally, we really need to start with discussion of events and thinking about what could happen before we do anything when we're looking at any individual question.